just to say, the email that you would have got last night, just saying the homework 2, question 2 was changed, by which I mean a third part. So homework 2, question 2, added a part 3. Maybe I shouldn't tell you which student's question prompted this addition to your homework, but let me say what the purpose was. So the original question was to sort of see that you can generalize the notion of Wick rotation to Euclidean loop integrals, even if you generalized from, say, a 2-point function with a loop in it to a Brazilian point function, an n-point function with a loop in it. That the basic idea of Wick rotation was there, but that the straightforward, just Wick rotate the Q integral that is natural to this, one of the propagators has a momentum Q, and we do the integral d4q, that Wick rotating the Q0 was not always straightforward. That you couldn't just rotate in the complex Q0 plane without encountering a singularity. In fact, in general, you do encounter a singularity. And that was the purpose of parts 1 and 2, although we were trying to notice that without any subtlety, ultraviolet divergences which occur because we're doing field theory and not quantum mechanics. In quantum mechanics, the only virtual quantity is energy. And all these things converge. Field theory is where you have this continuous infinite, if you think of X as think of phi as the analog of space, and X as the number of components of space, and it's a continuous infinity. This is what makes field theory different from quantum mechanics. It's the continuous infinity number of degrees of freedom. This is the same thing in Fourier transform form. It's this that gives us ultraviolet divergences when the Q goes to infinity. Not just this by itself, then everything would converge. And so the idea was to show that, at least for ultraviolet divergences, just Wick rotating the naive Q0 you get was good enough. That you could still Wick rotate for sufficiently large Q vector. But for smaller Q vector, in general, this Wick rotation gets messy in the direct attack. Part 3 is to show that suitably massaging it with the Feynman trick, or even calculating such integrals, allows you to do the Wick rotation in a straightforward way, not in terms of this Q0, but in some slightly redefined Q0 prime rotation, and everything works. So it's just an exercise in doing that, and also in just seeing the generalized version of the Feynman trick, okay, when you have many propagators. So this will hopefully make sense when you get to that point. Okay, so back to the action. So what I was saying last time with this analogy of the harmonic oscillator was that while they're the usual things that this is the wave function of the ground state, it's like this in X space. This is the energy level, which we usually often think of as being the state, but actually the state as a wave function looks like this. As somebody pointed out to me, yes, to make this look more familiar, of course, this is what we mean by this. And then there's some various other things that look like general. Okay, so all the wave functions are nothing but these overlaps. And I was pointing to this state itself, the wave function that corresponds to this state, which is some spike, or And we're familiar with this basis of x, the x basis, in quantum mechanics. We're less familiar with it in field theory, where the analog of these n states, which equals a dagger to the nth power, the analog in quantum field theory is various species of a daggers, E1, E2, E3, to some n1, n2, n3. So there are a whole bunch of different occupation numbers, but the sort of typical Fock space state is of this form. But I wanted to point to a wave functional, say, something that looks like this, and say, this, for example, is a, this is the amplitude, it's exactly the analog of this wave function thing you're seeing here. No, I shouldn't say that. This is the analog of something like this. It's basically the amplitude that the field measured at time t equals this 5x, which is a C number. And the reason that you can measure the entire field at time t is that phi, the operator phi, the Schrodinger operator phi of x, commutes with phi of x prime for all x and x prime spatial vectors x and x prime. Okay, so the fact that it's a Schrodinger operator, so I'm going to put I'll put the s, it's an operator, okay? The fact that this is true means that I can measure, I can find a state which diagonalizes phi at x as an operator, and also phi at any other point in space. This is exactly, so a state that looks like this. This space. That is a state which diagonalizes the field, the field operator for every point in space for a particular instant of time. Okay? It's the exact analog of this. Even if I had many components of space, I can still write this vector, this bra, cat, whatever, okay, the state. And it diagonalizes xi for every I. Because it's only x that doesn't commute with momentum. It commutes with other components of x. Similarly here, the phi does not commute with pi as a Schrodinger operator. So if I tell you that this is the wave function at time t, the next instant I have no idea what the wave function is, or wave functional is, or the state. I have no idea what the state is, or rather, I have no idea at this basis what it is. I can't tell you with 100% probability what this is going to be, okay? Because we have the uncertainty principle showing up in this form, but at a particular instant in time, I can tell you this whole thing. And it's just an unusual basis for this. So let me stop talking about it, except to say, build some comfort with this way of thinking and comparing it to this. But now we can reply, we can at least state what was the question that was answered. Because it's in this basis, the analog of this x basis, that we have got the answer, or we have phrased a question. Phi final, time order, this is space, or space alone. One of these kinds of states. That is the question, just like we used to have x initial and x final. And the answer has turned out to be proportional to, if you're being fussy, which we should be, just worry about it. Let's just say it's only proportional to phi of ti and x, initial or final, x is equal to phi initial or final. Okay, e to the I s phi. So this is where we had got to. And so we're supposed to look at all fields in space-time. So if you like, here's a picture of space-time. Time, space, and t final, t initial. And for this entire region of space-time, it's a little strip of space-time like this, I have to have this field phi. I'm summing over all possible fields. I'm summing over all possible fields that inhabit this, where on this particular line, phi equals phi final, and on this particular line, phi equals phi initial. So it's a boundary condition for this field. But then I have to sum over all fields, and since this is over time, we say a sum over histories of this C number field. It's crucial to say, the C number field. And that's the answer. Okay. So now we know what the question and the answer is. However, what we really like to do, this is not the question that we set out to answer. So we want to know, remember the generating functional? That's what we actually set out to answer, and we've got the wrong question. That's not this. So back to this. So the idea is to choose our h to be the h that you actually care about, whatever that is, phi to the fourth field theory, whatever Hamiltonian it is, go out there. But adding a source term. So short of just this. Note that this would look, from the quantum mechanics analogy point of view, like a potential term, but with a explicit time and space dependence. But we discussed that. Okay, that's why I'm writing time dependence in here. Okay, you might say, why didn't I write space dependence here? Because I'm integrating over space, so it's time dependence. That's what this is. Which is why I said, as an exercise, derive all these formulas just with a time-dependent potential. That's a time-dependent potential. Okay, so we know we have to get this in the game just if we're going to ever make contact with this. But there is this problem that we didn't actually want these initial and final conditions. In fact, the conditions that we want is we'd like to end in the far future with a vacuum. And we want to end in the past with, we want to start with a vacuum. And then we want to have this perturbation creating and destroying particles in some finite regions of space-time. Okay, so that's what we want. And so here's the trick for forcing this to fit into this form. And that is to add a slightly imaginary part to energy. This is energy. Normally it's Hermitian. Now I'm adding a slightly anti-Hermitian part to it with this prescription. And then I will cleverly take epsilon to 0 later and say that I did nothing too bad. But of course, the only reason for doing this is it actually does do something. What we want is that it does precisely the thing of getting us this instead of this, and no other harm. Okay, so that it's a surgical strike on exactly the thing that we want. You have to watch me to see that I'm doing it. Okay, but first I just say, let's do this. This seems like I'm totally changing the rules on you, but let's see whether I am or I'm not. You have to keep score. Okay. So, and epsilon goes to 0 later, but I'm not promising you anything yet. Let's see what it does. So, here's the expression I want to start with. This phi f. So what I mean by do this is I'm saying, here's the Hamiltonian. This H, which I just left as a general H, I'm saying it's your favorite quantum field theory H with a source term. So that's what this is. So that's why you see that. The second thing is I'm saying, let's do this seemingly illegal step, Hermitian. Hamiltonians were made Hermitian for a reason. So the probability is conserved, right? So I am definitely playing with fire, but I will do it. And so I'm doing that. But other than that, I'm keeping the question the same. So I'm just asking what this is. We don't know how to interpret it yet, because we don't like non-unitary time evolution. But whatever this object is, the claim is so let me not calculate it as a path interval yet. Let's just see what we can make of it. This thing is equal to, so I'm going to analyze the effect of this epsilon by putting in a complete set of states. Where these are H eigenstates. So basis. Now, H itself may be an interacting theory. Example 5 to the 4th or something. Field theory. I won't bother to write it out. It could be an interacting theory. So the energy eigenstates here are not the free field energy eigenstates, free particles. They're not. But, and therefore, I don't know how to get my hands on these, except doing perturbation theory and working very hard. But formally, they exist, and I'm just putting the complete set here in. And this is just the resolution of the identity, because it's an eigenbasis, a complete eigenbasis of energy eigenstates. So it's secretly just a resolution of the identity. So that's totally cost-free. And so we put this time evolution operator in again. And then I'm going to put in another copy of exactly the same thing. You recognize that very analogous to that kind of object in ordinary quantum mechanics. An energy eigenstate, in fact, this is just the ordinary harmonic oscillator. If it was an anharmonic oscillator, that could be the energy eigenstate of the full anharmonic oscillator. And then this overlap is a kind of wave function. Okay? Here, it's a kind of wave functional that is sitting on this side. Okay. So that's who it is. And I'm going to so, suppose J for some finite support, say J equals 0 for t bigger than tf, and t smaller than ti. Or maybe I should have said, say, only for t less than tf and greater than ti. So there's some region of space-time where my j is not zero. So maybe j may have support in a number of regions of this thing, but outside here I can count on it being non-zero. Okay. This certainly is not restricting our ability to function with these sources. If you want a correlation function for x1, x2, x3, x4, x, just choose ti and tf so that they are larger than the latest time of the correlator that you want, and earlier, and ti is earlier than the earliest time in the correlators that you're interested in. Okay. So this is not really a big restriction. So now we can see something that happens here, which is I need a different thing. Say, for t greater than t1 and less than t2. Okay, sorry. I've already used ti and tf as involving my question. I want to choose t1, t2. So t1 is greater than t initial less than t2, which is less than tf. Okay. So actually, I'm restricting my sources to, so here's t2. Okay, so my sources are non-zero in some sub-region of where I'm evolving these states between. Okay? And so for whatever j you really wanted, so again, these j's can be non-zero for very large periods of time to cover whatever correlators you ultimately wanted to calculate. And then I can choose my tf and t initial to be at even later times and earlier times than that. I'm going to do that. So in that case, this thing here breaks into pieces. Basically, in time evolution, I'm breaking into from here to here, here to here, here to here. Okay? And in the in the final region, from Tf to T2, it's e to the minus I h T2 minus Tf. Then there's this time evolution. Here are the three regions of time. On these outer regions, the source is 0, so the Hamiltonian is time independent. As long as the source is 0, the Hamiltonian is time independent. So therefore, all of this time ordered, blah, 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 you can forget about it. It's just this, time evolution operator, okay, as simple as can be. So now, so let me start on this side. E to the minus I h T1 minus T initial 1 minus I epsilon acting on, so you see it's all sandwiched between, say, an n prime here. So acting on an n prime. So this idea that we're going to take it to 0, this epsilon to 0 later, well, actually we're doing it by a sort of switch of limits. I want to consider epsilon non-zero, small, but non-zero. And I want to consider T1, Ti, I want to ask what happens as I make Ti very early, okay? So that this thing is sort of way down here. Here is the region in which I want to calculate correlators using these sources. But I'm now taking this thing to be very early. And if it's very early, then no matter what this epsilon is, this large thing overwhelms this small thing. And okay, so this is e to the minus I h T1 minus T initial. But this epsilon term is e to the minus h epsilon T1 minus T initial. Okay, well, this is an energy eigenstate, so I can just replace this by En prime, and this by En prime. So as Ti goes to minus infinity, it looks a little ill-defined. This thing is going around the clock many, many times. It's not clear that there's a limit, but there is, because I've got this guy, which is not oscillatory. It's got an e to the minus there. And this thing is getting bigger than this thing is small. So this whole thing is going to infinity. And so for any positive energy, this thing is just killing the state. Okay? This factor is going to 0. For any positive energy. Okay. And so maybe what I should have said was this is actually just equality. And this is as T1 minus Ti goes to infinity. And so find is this is 0 for En prime greater than 0, but it's 1, it's n prime if En prime equals 0. So if En prime equals 0, this is 1, this is 1, and I just get n prime back. And we work like sensible people who are not doing gravity. We work with energy calibration, such that E of the true vacuum is 0. This vacuum is defined to be the origin of energy. Okay? One second. And E of n prime not equal to the vacuum is positive. Yeah, question.
So this assumption that the vacuum energy is 0, is that, don't you only need that the ground state energy is lower than the next excited state, because that one will stick around longer than the other guys?
It will. It would just take me a few extra words to say so here there's there's a limit. See, I don't have to talk very much and say this is dominating over this as Ti goes. So just to keep things minimal, I'll just choose that convention, in which case you see there is a limit and there's not much to talk about, but I don't need that. Okay, so now we can see what happens to this. To be pedagogically correct, I suppose I should write an equation. So therefore, this phi f prime over e to the minus I rho Ti Tf dt prime hj prime 1 minus I epsilon phi I is equal to phi f vacuum goes as Tf goes to infinity, Ti goes to minus infinity. The same thing plays out on this side if I take T final to go to infinity, as opposed to T initial going to minus infinity, as you can easily check. And then I get okay. So one other thing I can do here is, I mean, logically, this is where we are. But let me just point out that without loss of generality, T2 equals infinity and T1 equals minus infinity. Can replace. Why? That seems a bit funny. Why? Because that seems to be like I'm including some extra time evolution from T2 to infinity, and from T1 to minus infinity. That's what I seem to be saying, and surely that's not right. But the evolution from T2 to infinity is with the sourceless Hamiltonian, which when acting on the vacuum is trivial, because it's the true vacuum. So this whole thing, acting on the vacuum, is a waste of time. Hence we can just add the extra, since we have time to waste. We have extra time from T2 to infinity and T1 to minus infinity where I'm not doing anything. So just to make it look cleaner, I can get rid of this T2 and T1 stipulation. Just put infinity and minus infinity. Okay. So that's that factor. But then we do have these phi f and phi I, these sort of arbitrary choices. You know, I gave you an example of phi initial sine x cos y and tan z or something. Who makes these choices? Well, the idea is that we're going to integrate over all possible choices of phi initial and phi final, and that is to do this. Where this is an integral over only functions of space. Only functions of space. Okay, so now we have to figure out what that might be. Let's do that. So note that integral the phi initial, say, of omega phi initial is equal to the So one way of doing a path integral like this would be, I have to integrate over all functions of x, but that's like sum over all possible functions of x. That's like summing over all functions of the Fourier transform of x. Okay, so let me work with the Fourier transform language and say, over all possible momenta, I have to do the Fourier transform So this is just another name for this measure. And then I have to do this. And now but of course, this is the interacting vacuum. Who knows what this is? It's a complicated thing, the vacuum in an interacting theory. But all I want to establish is that this is finite. Okay? This integral is not nonsensical. I'm not going to get infinity or something like that. And so of course the leading perturbative behavior is the Fock vacuum, like this. So basically, if this leading thing is finite, then I'll just have a series of little slightly deformed thing is finite. Okay. By definition of the word slight. But what is this? Okay, and that's where I use momentum space to make it easier, because the Hamiltonian, the free Hamiltonian, can be written. I can just Fourier transform the integral d cube x version of it, and I get the gradient term will just be so what you see is this looks, for every p, again, imagine discretizing the p's by putting everything in finite form for a second. Every p, it looks like I have a completely separate, I mean, this is a completely separable problem into every momentum mode. Every momentum mode is decoupled from every other one. That's why it's free particles. And everything looks like everything looks like a harmonic oscillator. It looks like there's a harmonic oscillator, P, the perfect analogy where the omega here is equal to this P squared, the omega squared is the P squared plus M squared. It's this harmonic oscillator analogy on which perturbative quantum field theories are based. So, the free Hamiltonian is a sum of harmonic oscillators, one for every momentum mode. But the integral I have to do is also just an integral for every harmonic oscillator. So this thing here looks like many copies. So it looks like many copies. I should say. Alternatively, the leading behavior is many copies of doing this integral. The vacuum of oscillator, the simple harmonic oscillator ground state of oscillator P, and this phi I P, which you should think of as, like in the simple harmonic oscillator, this is the position. The position in the pth direction. I, remember, just means the word initial. Doesn't mean index. Across the cover. P is an index, because there's an oscillator for every value of P. So that's the kind of integral I'm doing. Now, everybody knows that this is a Gaussian. We know what the ground state position space eigenfunction of a simple harmonic oscillator is a Gaussian that goes, I can't remember it exactly, but it's something like this. I mean, some constant, okay, like that, okay? So this integral can be done. It's clearly finite. It's perfectly good. Then you say, well, I have to take this product. Maybe I get an infinity there. Maybe you do, but we're regulating this as follows. We're willing to put things in finite volume in this course. That's not our problem. So having discretized momentum. But the momentum can get arbitrarily large, and so maybe something goes wrong. But again, we've got a couple of places where this issue has come up. We have basically got some subtleties in our discussion in path integral so far, all to do with short distances. Remember when, or short times. Remember when I did the path integral, I made it a finely grained picture of time, okay? But then at some point I said, look, I'm not going to keep writing out that everything is discretized time steps. I'm just going to say it's continuous because the time step is really small. Let's not worry about it, except later. So we already have that pending. Here too, I've effectively, to say, I'm saying, yes, there is some question of, okay, term by term, everything is fine, but for really short distances, that's really high momenta, so I'm taking this product, an infinite product. Does that make sense? That's again a short distance thing, which which is still pending, and I'm going to let it pend for a little longer. But other than that, issue of what about the short distance problems? Term by term, there's no problem. That's all I'm saying. So hold that question. I'll come back to that set of short distance questions. So therefore, but you might say, but don't I have to actually know that it's, so all I care about is that. But don't I have to know something more about it? And the answer is no. You see, again, we know that what's important in this object is the J dependence. This generating functional approach is the J dependence, which is everything. And there's no J dependence here or here. I was careful about that with all the T1s and T2s and all that. All the J dependences in this factor here. Okay? So I can simplify this whole thing and just write this thing is proportional to we're going to look at it a little more carefully, but this up to epsilon, so modulo epsilon subtleties, this looks like the definition of the guy we want, right? Remember how this was defined. I start with a vacuum, I have sources, I turn them on, I time evolve, back to the vacuum. Okay. Remember, whether you time evolve to when the sources are dead, or whether you time evolve to infinity does not matter. Because once the sources are dead, this is just the Hamiltonian, and this is the true ground state of the Hamiltonian, so the extra time evolution is not. Okay, so up to the epsilon subtleties and the short distance subtleties, what we're saying is that this is an expression for this. Now this is a weird object because it's got these integrals over functions of space only, and then it's got this horrible object. But actually this is the object for which we have a nice path integral expression. So we're about to look at how the epsilon, we derived a path integral expression for this without this issue of epsilon. Okay? We are going to look into the epsilon subtleties, but if you grant me that for a second, we have a path integral expression for this. So what does it look like? It says, therefore, that the thing we want is proportional to, with J independent constant. That's all I care about. It's proportional to the integral d phi I, the integral d phi j, up f. And then, if I didn't have this epsilon here, last lecture we had a path integral form for this, which I remind you is integral d phi, so here, these are the space. This is space-time, where phi equal to phi, or I, or f, e to the I s phi like this, and here we'd have this limit as tf goes to infinity, ti goes to minus infinity. I'm at the moment just going to write, we're about to look into it, I'm just going to say that, look, we actually didn't derive the path integral with this epsilon in place. So, whatever the modifications of this formula are, I'm just going to call it epsilon subtleties. It's our business to just look into it now. But let's just see where we're headed. So if you look at this whole thing of what you're integrating, T final, T initial, here is this phi. This phi equals phi f here, and phi equals phi I here. So there's sort of a boundary condition on this phi. But then the boundary value is itself being integrated. So it's as if you're allowing everything that can happen to this phi and this wedge to happen. And then furthermore, this TF is going off to infinity. But that means that you're essentially summing over, you are summing over every possible space-time field with no restrictions. Right? The only restrictions were these boundaries, which were themselves summing over all possibilities. And then that seemed to at least restrict you to a wedge of time. But now they're taking that wedge to infinity. So this thing is equal to the integral over all of space-time with no restrictions, just sum over all possible histories forever, okay, of the field. E to the I s of phi plus some epsilon series. It's very nice because everything here looks very relativistically invariant. There's no stipulations on time being final or initial or any of that kind of nonsense. Just all space-time scalar fields. The action, as we saw, looks manifestly Lorentz scalar. So it's all very nice. We just got to be really careful here. So you can actually sort of nail this proportionality constant by just remembering that the properly normalized eigenstate of energy, if you want a normalized eigenstate of energy, omega, should be normalized to 1. Okay? So now what do you do if a state is not normalized to 1? You divide by the normalization. So when I write this is actually a shorthand. This is not an overlap of omega with itself. This is shorthand for omega overlapped with itself, but with this big thing stuck in between. If I put j equals 0 here, in the same notation, once the j goes and the Hamiltonian acting on the energy is, on the vacuum is 0, it really, this whole thing is irrelevant, and I'm truly calculating just the inner product of omega with itself. I'm calculating the normalization of omega. So in a sense, this is the true, so maybe we'll like this. If your omega is already normalized to 1, then this expression collapses to this, and this is the thing that we want. Okay? If it is not normalized to 1, then dividing by this normalizes it to 1, and we are got the thing we want. Okay? This is what you're used to doing this. You have some wave function, and or you have some inner product where you have a state and another state, and you say, I want the normalization, then you would divide by the norm of the state and take the square root for each of the two states. Now here the two states are the same, so instead of getting the square root of the norm of each state, you just get the norm of the same state. So this is the object that we truly want. Even when omega is not normalized, this ratio gives you the normalized omega j. Okay? Now, if I just write that out, since this is a j-independent constant, it cancels out. So I can finally get rid of the damn thing, and here it is, that we have integral d phi e to the I s phi. And I'm just going to put a j there to say that, you know, if there was a j, I mean, there is a j in the Hamiltonian, it's going to show up in the action. And then integral d phi e to the I j. And then plus some epsilon. In both cases. Okay, so let's move on to those subtleties. But you can see the power of the approach is very manifestly Lorentz invariant rendition of the basic quantum mechanics problem that we face in this game for calculating correlators. All done in one line, identify a separate expression for every possible correlator of interest. It's all done in that. Okay, so epsilon subtleties. So, in a sense, the exercise to you, I'm just talking you through the highlights, but the exercise is go through the derivation of path integrals, formulation, with epsilon non-zero. In other words, you can even go all the way back to quantum mechanics, not even quantum field theory, but where the Hamiltonian is multiplied by this factor. Okay? Even in the quantum mechanics, the one-dimensional quantum mechanics. Just keep following through. And it's not really a big deal. You see, as far as all the manipulations we're doing are concerned, they are evaluating the given expression. They're not, there's nothing that we're doing which is putting in unitarity. We put in unitarity on line 1 by taking the exponential of the Hamiltonian. That's the question that we start with. And then we work out what the pathological version of it is. If you decide to start with a non-unitary time evolution, that's your business. The business of subdividing time and writing an operator expression like this in terms of C numbers, although at the cost of continuous infinity of multiple intervals, so there is a cost, but that can still go through step by step. And I just want to tell you where that epsilon would, if you just do this exercise, and you'll see that the epsilon shows up in certain places, and I just want to talk you through it. So epsilon shows up in, say, even the one-dimensional quantum mechanics, but and in every generalization of it. as a convergence factor in okay. Let me remind you of something that happened a long time ago, it seems now. We were doing one-dimensional quantum mechanics, and we kept inserting complete states in the form of the p basis and the x basis in oscillation, and we chopped up the time evolution in this way. And then it turns out, and of course we had to do a sum over these p's. A sum for every instant of time, we had to do one of these sums over p. This is one particular instant of time, t. If you want, think of t as being discretized. But there's a, go back in your notes, you'll see there's a point where the sum over the p's we could actually explicitly do. Because or rather, we said, imagine just doing it, because it was independent, this thing could be massaged so that it was independent of the things that we cared about, which are the x final and x initial dependence. Or when you have sources, it was independent of j. Okay? So we said, look, this integral, the sum over p's is just some constant independent of all the things I care about. So let it just go. Well, if we revisit that, it did look like this. And the way we said it was such a trivial integral was we completed the square for this pt. And then when we completed the square, we got something which was just a Gaussian in pt. But it was an imaginary Gaussian, e to the I pt squared. Okay? And I said, okay, it's a little oscillatory, but go ahead. Well, what happens when you have the epsilon? The epsilon is multiplying the Hamiltonian, right? That epsilon Hamiltonian. So one of the places it multiplies is the part of the Hamiltonian that looks like p squared over 2m. So that's why you now see it there. So as far as the p integral is concerned, the epsilon shows up there. It doesn't show up here. These came from these factors. There were a whole bunch of inner products like this. And then the next one would have been like this. And so on. And if in continuum notation you could, well, so you got a p times a delta x. And these factors don't care about epsilon. This is just the usual momentum and position bases. They don't care about the Hamiltonian. That's just the basis vectors, the basis states. So those overlaps, which give e to the I px, turned into e to the I p delta x terms. And a delta x you can write as an x dot, a kind of a discrete version of a time derivative times the delta t. So this is where this came from. You can go back and remind yourself. But the main thing that happens after you complete the square is you end up with something I call p tilde. Again, refer to your notes, where you've completed the square, and this is the part of the p integral that remains to be done. And all that's happened is that this epsilon is making the large p thing very explicitly converge. Okay? It's going like e to the minus epsilon p squared. Now epsilon may be small, but when the p goes to infinity, it does actually converge. So we get, now in the end, this is just a constant, but at least it's a finite constant, and we're throwing it away. Throwing it away is one of the many things that subsumed into this proportionality constant. Okay, so that's one place. If you do this exercise, you will see that one place the epsilon shows up, and clearly makes a difference. See, the epsilon is small, which means at first sight you say I should throw it away. The only place you should ever bother to worry about it is if it's competing with somebody who's large. Okay, then you have to care. When P gets very large here, there's a battle, and so we have to